In this video, I want to look at the review for the limit and continuity test, and this is some of the work that I asked you to do, encouraged you to do to get ready for this test. And here's the blank page. I'm going to go directly to the solutions, and I'm just going to kind of walk through that with you. Just to remind you, in order to earn an A on your test, these are the things that you should know and be able to do. You should be able to find a limit graphically, which includes the student being able to sketch the graphs of functions that you've experienced in the past in order to find a limit if necessary. You need to be able to find a limit analytically. And so the strategies for that are, first of all, you always try to use direct substitution when possible. And if that doesn't work, then you look to see if you can factor and remove discontinuities and then try substitution. You may have to use algebraic strategies to re-express the problem so that you can possibly remove discontinuities, like rationalizing the numerator or denominator, things like, well, the factor and reduce that we talked about. You need to know the two special memorized trig limits that we have talked about in class. You may have to use trig to rewrite expressions to find limits. If all else fails, you may have to sketch a graph, and particularly that's a good way to find the limit of or the continuity of a piecewise function. You need to know your horizontal asymptote rules so that you can find the right and left end behavior, or the as x approaches infinity or negative infinity. When all else fails, as again, sketch a graph. You need to be able to determine whether a function is continuous at a point, and very importantly, you need to be able to give the reason why a function is not continuous at a point. And remember, there are three reasons. One being f of c is not defined, or there's no y value. The second being the limit as x approaches c of the function does not exist. In other words, there's no limit at a particular value of x. And then the third reason would be that the y value is not equal to the limit, or stated, the f of c is not equal to the limit as x approaches c of f of x. You need to be able to find values that force a piecewise function to be continuous. To study, you want to review your notes, your warm-ups, your quizzes, and your homework, and do your review sheets. And then there are some extra problems in the book that you could do. I'm not necessarily assigning them, but it's just more practice, and some of you may want to do that. All right, let's take a look at this particular sheet, page 5 in the packet. I've provided the answers for you. In problem number 1, I'll just walk through these. I would probably sketch a graph of that function. We've talked about it in class. There's a discontinuity at x equal to 0, and the output to the right of 0 is 1, while the output to the left of 0 is negative 1. So you can see that the limit does not exist because the right and left limits do not agree. Now recall on your test, you may not write what I just said. You have to write the limit as x approaches 0 from the left is not equal to the limit as x approaches 0 of f of x from the right. Number 2 is a rational function. We know that there's a vertical asymptote at x equal to 1. Since there's a vertical asymptote at x equal to 1, the limit can't exist because of unbounded behavior. In problem number 3, the limit as x approaches a. X cubed is a continuous function, so we can use direct substitution, and I substitute the a and get a cubed. Number 4, the square root of x is a continuous function for x is greater than equal to 0. If we assume that a is 0 or greater, and I even wrote that in, then the limit would be the square root of a, where a is greater than or equal to 0. Number 5, we have a rational function. You can see that there's going to be a vertical asymptote. Hopefully you can see that at x equal to negative 5. So regardless of whether we approach negative 5 from the right or left, the limit will not exist by unbounded behavior. Number 6 is like the absolute value that we did earlier, except for this time, it's if you think about your transformations of functions, this is going to be shifted to the left 2 units, 1, 2. The output to the right of 2 will be a positive 1, and you can substitute values to determine that. The output to the left of 2 will be negative 1, so the limit does not exist because the left and right limits do not agree. In number 3, if we substitute 3 squared is 9 minus 6. Okay, so we have a discontinuity occurring at x equal to 3. So we're going to factor the denominator. There's x, and there's 3, and there's 1, and we want a minus and a plus. The x minus 3 is a removable factor, so we have a removable discontinuity. Now that we have removed the discontinuity, we can substitute 3 in place of x. There's a 1 left in the numerator, and we get 1 over 4. In number 8, we have another removable discontinuity. If you factor x plus 1 or x squared minus 1, the x minus 1's divide out. So now you can substitute the 1 in what's left over and get 1/2. Number 9, when you're factoring the sum or the difference of cubes, in the numerator we'll get x, the cube root of x cubed is x, the cube root of 8 is 2. Square the first term, opposite sign, product, always positive, and square over x plus 2 times x minus 2. The x minus 2's divide out. So I have removed my discontinuity. I can substitute the 2 in what's left over, and when you do, you will get an output of 3. Number 10. If you substitute 9, you get 0 in the denominator, so we want to rationalize the denominator by multiplying by the conjugate. That will give me the limit as x approaches 9 of, I'm running out of space here, I'm going to bring it down here at the bottom. So that would be the limit as x approaches 9 of x minus 9 times square root of x plus 3 over, in the denominator we'll get x minus 9, which divides out with the x minus 9, allowing me to substitute the 9 in the numerator, and that's where we get 6. In number 11, we're going to factor and reduce. Here's your difference of cubes again, and in the denominator we're going to factor out the x, and we're going to factor, reduce, and substitute. Number 12, we're going to try to factor and reduce, but you get x squared plus 4 over x plus 2 times x minus 2. So nothing is going to divide out. And recall, x squared plus 4 does not factor into anything. So in this case, we have to realize that we have a non-removable discontinuity, and our vertical asymptotes are occurring at x equal to negative 2 and x equal to 2. Therefore, as we approach an x value of 2, the limit will not exist because it's approaching its asymptote, and you could say by unbounded behavior as well as left and right do not agree. Let's see, number 13, the limit as x approaches infinity. Remember, this is about right in behavior, so we think horizontal asymptote. The degree here in the numerator and denominator is the same. So we're going to get the quotient of the leading coefficients, which in this case is 1. Now remember, that only applies when we're approaching infinity. Number 14, the limit as x approaches 2 is, we're going to factor in the numerator, x plus 2 times x minus 2. The denominator does not factor. Notice in this case, we're not approaching a discontinuity. If you substitute 2 in the denominator, you don't get 0. In fact, you get 8, which is perfectly okay. So this is just direct substitution. Number 15, we're finding the right in behavior again. So we're going to look at the degree, and the denominator is greater. So the horizontal asymptote is 0. So the function is approaching 0 at its end. Number 16, we are looking again for the right in behavior. So we're going to look at the degree. So the degree in the numerator is 1. The degree in the denominator is 1. It's the quotient of the leading coefficients. Negative 5 over 3. Don't get confused because the terms were not in descending order. Number 17, anytime we approach a constant function, we're going to always get that output. In this case, it's 9. Number 18, cosine is a continuous function, so I'm going to do direct substitution. The cosine of negative pi over 4. Remember, negative pi over 4 is in the fourth quadrant, and in the fourth quadrant, cosines are positive, and that refers to a 45-degree angle, and the cosine of that would be root 2 over 2. The limit as x approaches 0, tangent is the same thing as sine of x over cosine of x. The cosine, if we substitute 0, the cosine of 0 is 1, and the sine of 0 is 0. 0 divided by 1 is 0. Number 20, limit as x approaches 0 of sine x. We're just going to substitute 0, direct substitution. Number 21, e to the x is a continuous function. We're going to substitute 0. E to the 0 is 1. Number 5, we're going to do direct substitution, and we get 1. Number 23, we're approaching a discontinuity, so I'm going to get a common denominator, which would be x minus 1. Well, it already is the same denominator, but I'm going to put it together. So that's x squared minus 1 over x minus 1. I can factor, remove the discontinuity, and then substitute the 1. Number 24, I can use direct substitution. The square root of 16 is 4, and the fourth root of 16 is 2. Number 25, I cannot use direct substitution, but I can multiply by the conjugate, so that would be 4 minus 16 plus h over h multiplied by 4 plus the square root of 16 plus h over 4 plus the square root of 16 plus h. Multiply that together, remove the discontinuity, and then substitute in 0. I'm running out of space here. Alright, let's look at the next page. We're using a graph to find the limits, and in this case we're finding f of a, we're finding the left limit and the right limit and the overall limit. We're looking at the continuity. Be careful to remember that the limit does not necessarily equal to the y value. Let's see if there's a case where that goes on here. Well, we have kind of a case right here at negative 1. The actual y value, f of negative 1, is 1, but the limit does not exist because as we approach from the left and the right side, we're not getting the same y value. So the function is not continuous there because the limit as x approaches negative 1 of f of x does not exist. As we approach positive 1, notice what happens here. There's no y value, but the limit does exist because we are approaching the same y value from both sides. However, the function is not continuous because f of 1 doesn't have a y value. The next set, we are finding constants a and b that force the function to be continuous. And you can see in my work that I substitute the breakpoint negative 1 in letter A and force the y values to be equal and solve that. Letter B involves a system of equations, and I don't know if you can read this. This is negative 13 over 6. So basically you can look at my work to figure that out. In problem number 3, it's the same thing we were doing with limits, just a few more. Here, let me keep that. And you can, I'm not going to talk through all of these like I did the other ones. However, you can freeze the video and take a look at my work and figure out what your questions are. So these are some samples of kinds of things that you should be able to do on your test.